Hello, let's start with one of the most essential foundations of HVAC design. Whether you are designing a small office or a massive commercial complex, knowing how to estimate heating and cooling loads is your starting point. In this video, we'll introduce you to the key concepts that drive those decisions, from what thermal loads really mean to why understanding them is crucial for comfort, energy efficiency, and system performance. Get ready to dive into one of the most fundamental concepts in HVAC system design. In this video, you'll discover what heating and cooling loads really are and why we refer to them as thermal loads. We'll break down how and why these loads fluctuate throughout the day and how different factors from solar radiation to thermal mass shape and how HVAC systems need to respond. By the end, you'll understand not just the definitions, but also how thermal loads behave and why that matters for comfort, energy efficiency, and smart system design. Let's get started. Here's what you're going to take away from this video. You'll be able to clearly describe what heating and cooling loads are, spot the difference between heat gains and actual HVAC demands, and understand how thermal mass influence when these loads actually impact comfort. These skills are essential from any HVAC designer and will be your first step in mastering load analysis. Before we go deeper, here's something to think about. How will you estimate the heating or cooling needs of a building you have never worked with before? So, will you look at the materials, the orientation, or something else? These questions opens the door to understanding how real-world conditions shape HVAC design decisions. In HVAC design, heating and cooling loads describe the amount of heat that must be added or removed to keep indoor spaces comfortable. A heating load is the heat a building loses and needs to regain to stay warm, like on a cold winter night when warmth escapes through the windows and walls, and the heating system must make up for that loads. A cooling load, by contrast, is the heat a building gains and must expel to remain cool, for instance, when sunlight streams in during summer and raises the indoor temperature. Understanding these loads is essential for HVAC system design. Accurately estimating them ensures the system is neither oversized, leading to inefficiency and extra cost, nor undersized, which cause discomfort and strain on equipment. These loads aren't static. They vary with a building's orientations, materials, use, and even the climate. That's why a strong foundation in this concept leads to better decisions and more efficient designs. In this slide, we examine how heat gains and losses relate to thermal loads in buildings. Heat gains represent all the ways energy enters an indoor space. For example, solar radiation entering through windows, heat from lights and computers, or warm air coming in through cracks and leaks. Heat losses, on the other hand, occur when energy escapes from the building. This can be through poorly insulated walls or windows, or when cold air infiltrates the space from outside. These gains and losses affect the indoor temperature. When they push temperature outside the comfort range, the HVAC system must intervene, either by adding heat to counteract losses or by removing heat to counteract gains. This myth to correct temperature imbalance is what we call the thermal load. Thermal mass plays a key role in building energy dynamics. Material like concrete, brick, or adobe absorb heat during the day and release it slowly over time. This buffering effect creates a delay between the moment heat enters a building and when it actually warms the indoor air. As a result, the cooling or the heating load may occur hours after the actual heat gain. Let's take solar gains as an example. While sun radiation may peak at noon, The cooling load inside a concrete office building may not peak until 2 or 3 hours later, once the stored energy starts warming the indoor air. Similarly, if a room full of laptops and printers powers on at 9 a.m., the peak cooling load may occur much later in the day. Recognizing this delay is essential. HVAC systems should be designed not just for the time of maximum gain, but for the time when the gain translates into a real cooling or heating demand. This is what ensures occupant comfort and energy-efficient system performance. This complex explains why lightweight extractors experience more immediate temperature swings, while massive ones offer thermal stability, often making them more energy efficient when combined with smart HVAC control. So let's wrap up what you have learned in this video. Heating and cooling demands, or thermal loads, are a fundamental part of HVAC system design. These loads are not fixed. They vary depending on factors like solar radiation, internal gains, infiltration, and building materials. We explore how thermal mass introduces a time lag between heat gains and when those gains actually affect indoor comfort. Understanding this delay and recognizing that thermal loads are dynamic and context dependent helps you design more efficient and effective HVAC systems. This video laid the foundation for everything that comes next. You now understand what thermal loads are, how they behave, and why they matter. In the upcoming videos, we will explore specific sources of thermal loads like people, equipment, and solar radiation, and see how design decisions influence their impact. Later on, we'll move toward advanced topics like load control strategies and refined estimation techniques. Stay with us. You are just getting started, and the best part of your HVAC journey is ahead. Thank you.